Okay, so Kobayashi-san talking about phase-space structures, please.
Thank you so much. So today I'm going to be talking about phase-space turbulence in magnetically confined plasmas. I'm from National Institute for Fusion Science, Japan. So this is outline my talk. First of all, I will talk about the background of the study, especially focusing upon the phase-space turbulence and why they matter for fusion development. And then I will talk about our approach for measuring the phase space perturbative structure in large helical device, which is an steroid device in Japan. So I will talk about the diagnostic principle of charge exchange recombination spectroscopy and this upgrade for the fast frame rate diagnostics. Then I will talk about our analysis methodology, which is called phase space tomography for reconciling the high resolution in velocity, space, and time. Then I will talk about the result which we obtained, which is a bifurcation in distribution function deformation. And if I have time, after that, I will talk about new direction, which is a Bayesian statistical analysis for the velocity distribution function. And I will summarize my talk. So first, background. So this is a convention of the turbulence study in fusion plasmas. Of course, we study the turbulence to understand the plasma transport property in fusion devices like existing devices and also the future devices like ITER. In that context, the wave-wave nonlinear interaction plays a role for the turbulence development and also the turbulence saturation and also the flow drive, which in turn regulates the turbulence and making a self-regulating system. And as we have discussed in the previous talk and previous two talks, and phase delay between fluid quantities like density and turbulence, density and temperature, and potential could be a source of instability, which is called non-adiabaticity as shown here. And the non-adiabaticity originates from for example, collisions or trapped particle motions and others. And in this context, the wave-particle interaction is often or sometimes treated as linear, and lambda damping or such kind of wave-particle interaction is considered. Then I will talk about the phase-space turbulence. Phase-space turbulence becomes very important when, especially, the wave creation times becomes longer than the collision time or bounce time of the trapped particle, especially in the high temperature plasma where we have less rare ion-ion collision. So in such a case, the particles that are trapped in a wave can non-linearly influence the wave field, which is illustrated in this picture. So let us consider the blue curve here is a propagating potential wave, and black curve is trapped particles into a wave phase of the potential wave. Because those particles have similar velocity compared to the phase velocity of the propagation wave, the particle cannot go beyond the wave potential. Once this happens, the local deficit of particle can happen, which can enhance the wave amplitude because this can be a charge separation, a charge accumulation. Then the enhanced wave can affect the number of particles that are trapped. Then the local deficit of particles can be enhanced further. This kind of self-regulation of the wave and the particle, which is nonlinear, can be considered as a source of phase-space turbulence. And if you draw the trajectory of the trapped wave and the passing wave, so trapped particles and passing particle into the wave into the phase space, which is a span between the real space and the velocity space, you can draw up the vortex-like structure, which is called VGK vortex. And this kind of VGK vortex sometimes can be seen as a whole structure of the Maxwell distribution function as shown here. So this is why this kind of structure is sometimes called the phase space whole. What's more, this kind of phase space whole can evolve into the turbulence field as shown here. This is an result of the one-dimensional Vlasov simulation, starting from the single vortex, which evolved into the turbulence field. once this happens, of course, there can be a transport which is driven by phase space turbulence, like drift wave turbulence. But since this is intrinsically nonlinear, the driven transport can have a very qualitatively different feature compared to the drift wave turbulence driven transport. So they are, of course, very matter for fusion development. So what I'm showing here is a definition of the fusion gain Q, which is given by fusion output divided by fusion input. And fusion, input power, which is necessary to sustain the plasma. And denominator can be substituted as by the loss by transport minus alpha heating coefficient. And of course, to gain high Q value, both decreasing loss by transport and increasing the alpha heating coefficient must be achieved. Of course, the phase space turbulence affect significantly for both processes like turbulence transport and alpha heating, especially for the turbulence transport. The phase space turbulence or phase space structure can release energy from the real space gradient as the case of drift wave turbulence, which drives the transport as well, but this transport is qualitatively different from drift wave. So this can be a clue to resolve the turbulence unresolved questions in fusion devices. On the other hand, if you focus on the alpha heating, the phase space turbulence or phase space perturbation can affect both the energetic particle transport and also the bulk plasma heating through nonlinear random damping via wave, which is driven by the energetic particle. So competing processes between these two is very important to estimate the plasma parameters. So this is very important. So understanding of the phase space dynamics is very important to predict those two processes. So today I will focus especially upon the the wave particle interaction between energetic particles and wave. So let me go more in detail about the alpha channeling. So alpha channeling is a scenario where the fusion byproduct alpha sustains the plasma by heating the plasma. So due to its high energy of the alpha particles, the bulk electrons rather than ions are selectively heated. And collisional energy transfer from electrons to ions is far less efficient in collisionless plasmas because collision is quite rare. And what's more, the situation that the electron temperature is larger than the ion temperature is not desirable for the turbulence transport. So direct energy transfer from alphas to bulk ions mediated by waves and not mediated by electrons is desirable, which is called alpha channeling. So this is quite beneficial scenario, and many studies are dedicated for the alpha channeling or energetic particle channeling. Let me show some example of the energetic particle channels, which is obtained by MHD kinetic hybrid code, which is called MEGA, for reproducing the dynamics of the bulk plasma and energetic particles, respectively. What I'm showing here is a time evolution of the frequency spectrum, which shows a coherent and chopping up fluctuation structure which corresponds to the gamma. And once energetic particle driven gamma appears, the bottom plot shows the energetic particle lose energy and ion and electrons get energy. So this is energy exchange between bulk plasma and energetic particle mediated by gamma, mediated by wave. And this is one of the example of the energetic particle channeling. What I'm plotting in left is the phase space perturbative structure around the gamma channeling is occurring. So we see a complicated fluctuation structures around here, like Hall structure and clamp structure, which also evolve in time. And this is considered to be a recipient of energy from energetic particles. So this perturbative structure is very important to determine the efficiency of the energy exchange between energetic particles and bulk plasmas. So there are many this kind of simulation study, but this number of experimental measurement is reported. So in this work, I will discuss the experimental measurement for this kind of phase space structure. But this is very challenging, of course. So let me discuss why they are so challenging. This is because time resolution must be better than the ion collision time, which is typically 10 kilohertz, and this is very challenging. Especially a trade-off among real space, velocity space, and time resolution must be accounted. So let me deepen this point using this illustration here. What we usually do to measure the fluctuation components distributed in space is shown here. So what we do is we just divide the space into a regular subdomain, and we quantify the signal intensity in each domain. In order to make it for the phase space diagnostics, we have to extend an additional axis in vertical direction of this figure here, and we have to distribute the signal intensity in this sampling bin into the additional coordinate, which makes the signal intensity in single sampling bin smaller and smaller. And this makes the diagnostics very difficult. What we have to do to have a meaningful measurement is that somehow we have to abandon the resolution, for example, in the velocity space or real space or time space to get the high enough signal intensity. This we call the trade-off. Of course, there are another point which makes the diagnostic difficult. For example, multi-channel detectors with high frame rate and low noise level are very difficult to obtain, and it can be kind of very expensive. And also limitation of diagnostic principle is also there. So not so many kind of diagnostic principle can give us a velocity space resolution. Then let me talk about our approaches in LHD. First of all, I will talk about the background diagnostic principle of charge exchange recombination spectroscopy. Our target light emission is the charge exchange emission of the carbon impurity or any kinds of impurity, light impurity. However, inside the plasmas, most of the light impurity is fully stripped and doesn't have any electron. Then visible emission doesn't happen in such a case. However, inside the volume of the neutral beam injection, the carbon ions can get electron by the charge exchange recombination reaction. Then the subsequent decay gives us a line emission. And line emission is affected by the ion motion, giving us information of the velocity distribution factor. So plot in the right is an example of the obtained spectrum, which can be used as a proxy of the velocity distribution function. So let me show a practical example of the measurement of the CXS in LHD. So first of all, I will talk about the conventional system. So what I'm showing in the left is the toroidal cross-section of LHD. So we have elongated or elliptical shape of the toroidal cross-section. What I'm showing as a gray dot here is a projection of the line side of our charge exchange recombination spectroscope. So we have totally 100 channels in the radial direction and 15 channels in the vertical direction. And the blue dot here, light blue dot here is the channel which is used for the conventional charge exchange. So bottom plot here is an example of the ion temperature measurement, which gives us a very smooth and high resolution radial profile of the ion temperature. So far, so good. But this is not directly applicable for the measurement of the distribution function deformation, for example, induced by the energetic particle-driven MHD burst event. The right-hand side figure is a time evolution of the toroidal magnetic field fluctuation and velocity distribution function measured by the conventional system. Because of the longer exposure time of 5 milliseconds, we cannot decompose the velocity distribution function evolution caused by the MHD burst event, which lasts 2 to 3 milliseconds. In order to improve this situation, we developed a new charge exchange recombination spectroscopy system, which has a shorter exposure time of 0.1 millisecond, such that we can decompose the time evolution of the velocity distribution function caused by image debug. What we have done is shown in this slide. To have a high enough signal intensity to shorten the exposure time by 50 times, we integrate the signal from the different states. That's why we can get this kind of fast measurement. In other words, we abandon the signal, we abandon the spatial resolution to have a high time resolution due to the trade-off. So this is an example of the trade-off. Still, we can get a very nice result of the wave-particle interaction using this new diagram. The left-hand side here is the velocity distribution function before and after the energy burst event. So before we have Maxwellian distribution, but after we have a decrease of the particle number around the zero velocity and increase in particle number in the tail component, which have a zero crossing point here, which corresponds to the resonant velocity of the wave-particle interaction. The right-hand side here is the relation between this resonant velocity and also the wave propagation velocity in toroidal direction, which is measured by the toroidal magnetic field array. So we see very clear linear relation between these two. So this is a signature of the occurrence of the random number. And also the velocity changes in time. So this is clearly nonlinear, and this is an evidence of the collisionless energy exchange between bulk particles and energy particles. Yes. What is the Alphen? Well, Alphen speed is very fast compared to this phenomenon. So this has a kind of 2 to 5 kilohertz in frequency, but Alphen frequency is much more, kind of 10 times larger. And I think we consider this is kind of interchanging instability, which is driven by energy particle.
Is there some reason why the resonance structure is so conveniently one-dimensional in toroidal geometry? I mean, you really have a combination of the Landau and the drift, right? So, I mean, how they get to make a picture that looks like what we all learned in graduate school, right? About BGK modes and 1D. How does this miracle occur?
Well, so this is very, I think, still very challenging. So this is what
I know that.
Yes. Yeah, if we can do that, it's very wonderful.
But I mean, in some sense, there must, for this to mean anything, there must be some aspect of this problem that basically reduces to a 1D structure. So could you explain that?
Yes, one possibility is to use the linear device or some basic device which has a one-dimensional magnetic field. Then we can use a velocity distribution function measurement using electrostatic probes and kind of elementary diagnostics. This is one approach, but this has been done maybe 20 or 30 years ago in linear device. But with conventional considering, then we can update this kind of. Yes,
but maybe in this case, these were trapped particles. In tokyo-lax, very often the resonance is with trapped particles.
Yes,
it's
very trapped particles. Yes.
Yes, then it's one dimension because it's p zeta is the space.
Yes.
Precision angle, right? So it only makes it one dimension.
Yes. But the point is that it's very difficult to have a toroidal array of line of sight for the This is why we cannot make such kind of. Yes, but in linear devices, it could be possible. So, thank you. So this is very good, but we abandoned the spatial resolution instead of the time resolution. So we need to somehow improve this situation. So we apply the phase space tomography for resolve this. So as I said, it's very challenging to measure the F2 component as a function of log T as a single diagnostics. However, obtaining 3 integrated data is possible integrated data are possible as we have discussed in the previous slide. So by combining these different data, we try to deduce the original structure of F2. So let me show an example of the three-dimensional tomography in real space. So we have our object here. Then we have three different layer sides having three different two-dimensional images. By combining the three images, we can try to depict the original structure in 3 dimensions. We will apply this consideration into the space. We have velocity space and real space time, and we can have 3 different integrated diagnostics, which correspond to the flow sheet space, which we have introduced in the previous slide, which is time integration, but velocity and space resolution. And another one could be a path shape space, which has a space integration, but has a velocity and time resolution. Another one could be a line intensity measurement, which has a velocity space integration, but this has a resolution of space and time. And we try to combine these 3 to reproduce the original structure. And this is a numerical test, and we confirmed that this works quite well for our target plasma perturbation. And let me show an result which we have obtained. And this is our target discharge. This is a time evolution of plasma parameter. The top figure is the heating power of neutral beam, which is injected perpendicularly and parallelly. And perpendicular injected neutral beam is used as a probing of charge exchange recombination spectroscopy. So we intentionally modulate this power to reduce the background emission. And black one is the heating power of the tangential NPN. And this sometimes experiences the natural breakdown. And we use this natural breakdown for the power scan experiment in our data. And second and third figure is the time evolution of the colloidal magnetic field fluctuation and our clock signal, which has a varsity activity which corresponds to the energy path-driven image event. And we got 10 discharges for making the data set, and we have totally 145 this kind of event for high power period and 187 events for low power period. And we apply the conditioning average to reduce the noise and to apply the phase space tomography. Let me show the result of the phase space tomography for the high power case. This is quite similar to the previous observation. As I said, we have decrease in the particle number in the zero velocity region and positive tail after the energy burst event, which is shown by blue and red color here. And this is the time revolution of the phase space perturbation structure as a function of velocity and time. So this is three-dimensional perturbation structure. And we have a symmetric positive negative pair of velocity distribution function, which disappears in the collisional time scale. So this is what we can imagine from the integrated data as well. However, if you look at the low power case, we have something more interesting. If you look at the point at 4.41 seconds over there, we have something similar to the previous event. So we have single positive negative pair of extruder component with a single resonant velocity of the positive direction. However, if you look at the case at 4.45 seconds, we have another tail component in the negative direction. This gives us 2 different resonant velocity at positive and negative velocity region. So this kind of bifurcation can be seen in the low power discharge. So let me discuss the statistical property of that bifurcation. So what I'm talking here is extruder component at different event like numbers like this. So for example, if you look at the case of number 40, you don't have any negative tail here. But if you look at the event 41, you will see a negative tail. In order to quantify whether or not this negative tail appear or not, we just count up number of the negative number of particles inside the negative tail by making an integration over here. And I made a PDF analysis for the number of particles that are negatively accelerated on this. The powerful case is the high power case. So we have single peak PDA having a peak close to 0 because this corresponds to the occurrence of single resonance. However, if you look at the case of low power case, we see an additional peak in the high value of particle number, which are negative accelerate. This corresponds to the occurrence of the negative tail or dual resonance. And if we can count up the number of events for single and dual resonance, we have 92 and 56 number of events. So let me apply the phase space tomography for the single and the dual resonance. So we don't see a slope here, but for the single resonance, we have negative positive pair of extruder component as a function of how rho, so velocity times space. And for the case of dual resonance, we see an additional structure in the negative velocity region of extruder component. The bottom plot here is a time utilized at 0.5 millisecond after the energy burst occurred. So what's interesting is that the location of the positive resonance and the negative resonance different. So positive resonance occurs more inside and the negative resonance occurs more outside. And time of occurrence is also different. So the negative resonance occurs delayed to the occurrence of positive resonance, which should be shown in the slide, but we cannot see. But anyway, so the occurrence time and the location are different. So finally, let me confirm what is happening for the wave field by looking at the magnetic field fluctuation measured by the toroidal array of probes. So this plot is a time and space, so toroidal space plot. So in the case of single resonance, we see a plane wave propagation in the positive toroidal direction, which has a same phase velocity compared to the resonance velocity. So this is quite consistent. So this is relevant to drive the wave pattern interaction. If you look at the case of dual resonance, you don't see any simple propagating wave, but very complicated wave field that's found. And if you apply the two-dimensional Fourier analysis, you can see a positively propagating wave component and a negatively propagating wave component, which has a corresponding phase velocity to the negative and positive resonance. So this is also consistent. Finally, let me discuss possible interpretation of the bifurcation. So resonance condition in helical device is quite complicated because of the existence of higher order magnetic Fourier component that can provide a multiple resonance. This is shown in this equation. So the original energy source of the energy particle stability is conserved with a helically trapped energy particle propagating this way. But because of the geometrical factors shown here, this resonance frequency can be either negative or positive. So bifurcation in this case is considered here to be a selection of the resonance condition to the multiplication of the resonance condition. So this is a discussion. So somehow properties of fusion plasma sensitive to the resonance condition. So this is time evaluation of the net energy gain for the single and dual resonance cases. Of course, we have both positive and negative tails. So the dual resonance has a better energy gain compared to the single resonance. So this higher net energy gain due to efficient energy transfer from magnetic energetic particles to bulk plasma is a signature of the dual resonance. And the resonance condition, so likely the confinement magnetic structure directly affects the plasma thermal properties. So I will quickly go through the new direction. So the discussion so far has been based on the measured spectra. However, the emission spectra basically reflect the velocity distribution function, but they are not directly identical. There are several reasons that makes the distribution function and the emission spectra different. For example, the shift due to the ion gyro motion of the carbon ion, and also the spectral broadening by instrumental function. So inferring the velocity distribution function from measured spectra is kind of an inverse value problem. So direct conversion from the spectra to the velocity distribution function is quite challenging, especially we consider that the velocity distribution function is not Maxwellian. So we try to use the Bayesian optimization to do this. And this is based on the Markov chain Monte Carlo sampling. So we apply different kind of set of input distribution function to the forward model, which gives us a model of data. And by comparing this to the experimental data, we try to estimate the velocity distribution function by use of this technique. And this is ongoing. So let me summarize my talk. So importance and difficulty of the phase space turbulence study were discussed, and recent progresses in the diagnostic development were shown. And phase space tomography for reconciling high signal level and phase space resolution was proposed. And phase space tomography was applied to energetic particle-driven instability MHD event, and different set of phase space distortion were shown, and perspectives were discussed. Thank you so much.